So I think we're finishing up section 2.5 with some definitions. Those definitions are transpose, symmetric, and skew symmetric. Okay, and so a transpose, if we let A be M by N, defined by A is, this set of IJs, then this thing we call a transpose, or the transpose of A, transpose of A, denoted by typically either a T superscript like that. It could be an uppercase T. Your text uses the lowercase t. Or you'll see it just as a prime, kind of like when you see derivatives. You might see it as a prime. So any of those might be talking about a transpose. So denoted by this is given by a transpose equal, and all you do is, oops, well, that's what you do, but I didn't do it. All you do is switch the rows and columns of A. So, a couple of examples. If A is 1, 2, 3, and then 4, 5, 6, then A transpose, take the first row, make it the first column, take the second row, make it the second column, and there's A transpose, right? So if A is M by N, A transpose is N by M. Okay, so that's kind of neat. And so, looking at this and some properties, right? One, A transpose is just back to A. I think that makes sense. If I add or subtract A plus B and then take its transpose, well, I could have taken the transposes first. And again, I think that seems pretty straightforward. If I have a scalar multiple, I can just factor that out, do the A transpose separately. Now you get into the multiplication, and it's a lot like the inverse idea. So if A times B is defined and I want the transpose of that, that's B transpose A transpose. I have to reverse A and B to get that. And so, if as they point out in the text that, say A, right? A is M by N, B is N by something else. Now, those two, the N and the M, have to match up, but then notice A transpose is N by M, and B transpose is P by N. And so, in the same order, A then B, you couldn't do that multiplication necessarily because M might not be equal to P. But, B transpose A, right, that's, A transpose, that's the P by N times N by P. This is P by M. Whereas the AB, right, up here, we can toss that in, AB is M by P, right? So those swapped. Let's see, and then a very nice property is that if A inverse exists, okay, if A is non-singular, then if I want the inverse of the transpose, that is just the transpose of the inverse. Now there is a nice property, right? So if I have A and A inverse, and I want A transpose and A transpose inverse, I've got all I need. I can just swap things out. And then finally, 6, if X is a vector, then if you take X transpose X, what you get is, you get this X1, X2, X3. So typically you think of this as a column vector. So I better say that is a column vector. Because if it's a row vector, well, no, this wouldn't work this way. The dimensions would be different. But if, you know, up to xn, and then times x1, x2, x3, down to xn, like that. Right? If you do that, that's just this dot product of that row and that column. So you get x1 squared plus x2 squared up to xn squared. So what you see then is this is equal to the magnitude of x squared. Okay, so the magnitude or the 2 norm of x squared. And so that is a very convenient property right there. Okay, so those are transposes. Then we've got symmetric. And the reason we do transposes before symmetric is that A doesn't look like an A to me. Try that again. A is symmetric if A transpose equals A. Okay, now notice what that means is, well, A is square. It's n by n. Right? Because otherwise there's no way the transpose could be equal to A. And another way to look at this is if A is then, you know, Aij, what this means is that for each component Aij, it's equal to Aji, right? If I switch the row and the column, I get the same number back. Okay, so when you look at a symmetric matrix, you know, so an example of one might be A, B, B, C. Okay, because then A transpose, I take the first row, that was AB, make the first column, take the first second row, make it the second column, BC, right? I get A back. So that is symmetric. Now, what's interesting though is that no matter what we have for A, right? If we take the matrices either A transpose A, that matrix, and if we did A transpose, that matrix, these are both symmetric. Okay, and we can just see it with A transpose A, right? If I let B equal A transpose A, then B transpose is equal to A transpose A transpose, but that's equal to A transpose transpose. Okay, so I reversed the order of those two and took their transposes, but that's A transpose A, and that's B. So if I multiply A transpose times A, I get a symmetric matrix. So that's nice. Okay, skew symmetric. In this case, skew symmetric, we have that A transpose is equal to minus A. Now, of course, this again implies A is n by n, but another thing it implies is that AII, the diagonal, has to be 0. Okay, because in a transpose, the diagonal elements are all remain unchanged. They're in the same spot. Well, so the only way for the negative of AII, right, we need the negative of AII to equal AII. Oh, well, that implies it has to be 0. And so what happens here is then those are all 0, and then any AIJs, that's the negative of AJI, where I is not equal to J. And that is a skew symmetric matrix. Okay, so an example they give is just, something like 0B, negative B, and 0. Okay, now, so what happens if I take a skew symmetric matrix and do its transpose? Well, back here I said for any matrix, if I take A transpose A, that new matrix is symmetric, not skew symmetric. So, suppose A is skew symmetric. Let's see what happens when we do that. Let's define B equal to A transpose A. Then B transpose is equal to well, if A is skew symmetric, let me just go with this is B is equal to negative A squared, I guess. Okay, let's look at B transpose then. B transpose is I'm trying to think if I don't know if that's really helping me or not. So let me just go with B transpose and do it as I did before, A transpose A transpose, and just kind of see what happens. But notice that B is indeed minus A squared. Okay, doing the transpose thing again, we get A transpose and A transpose transpose. Now, just for the heck of it, let me do that as minus A. And let's do this as minus A transpose. But minus A transpose, that's just a scalar. Bring the scalar out. And so I have a minus and a minus. So that makes a positive. So I get A times A transpose. But A transpose is negative A. So this is A times negative A. And I get negative A squared. Okay, so again, which was B. And so you can see that, this comes out this way. So that's interesting that, with a skew symmetric, when you take a squared, when you do this A transpose A, you get negative A squared. Whereas with a symmetric, if you do that, you'll just get A squared. Let's see. Now they have a couple interesting, another interesting result here. Their corollary I'm having trouble spelling. Try to do that again. Okay, corollary. Okay, corollary 2.5.4. And this is kind of interesting, is that if B is skew symmetric, then A equal the identity minus B is non-singular. So that's very interesting. No matter what B is, if it's skew symmetric, then if I take I minus B, I get a non-singular matrix. I get an invertible matrix. And so then what they do is they look at x equals 0. Okay, so they want to solve that, but what we know is if that only has the trivial solution, then it must be that A is non-singular. So that's what they're shooting for, okay? Is that AX equals 0 implies X is the 0 matrix. So that should be 0. And, okay, so they do that, and they set AX equal to 0. But you see, we just use what A is, and that says that this implies, right, that I minus B times X is equal to 0. Okay. Now, so I can multiply that through. That implies that X minus BX is equal to 0. Okay. And so just moving the BX to the right-hand side, the vector X is equal to B times X. Okay, and now they multiply through by the transpose. So X transpose X is equal to X transpose B times X. Okay, now, so what they do is they switch sides and take transposes. So they write it this way. X transpose X, like that, and then they take that transpose. Well, that has to be equal to X transpose X, all transpose. Now, X transpose X, that's a real number, and the transpose of a real number is just that same number. You could also do it by going through the properties. But let's look at both sides here. We have, so we reverse order and take transposes. on the left here, so that's X transpose, B transpose, and then X transpose, transpose, so 2 transposes, so I just get X back. And here, I just get that same thing. Again, if I reverse order, right, I've got X transpose, and then the transpose of X transpose. Well, so that's just X. And so we get that. Okay, but B transpose is negative B, so on this side we have minus X transpose B times X is equal to X transpose X. Now, here's the thing. Here, notice back here, sorry. Okay, we have that, and we have this. So what this says is that if we call this X transpose BX some real number R, we have that X transpose X is equal to R, which is equal to negative R. Okay, they're both the same. Oh, that implies that X transpose X had to be 0. Okay, because again, this is a real number. Now, this is a real number. You might want to convince yourself of that, right? I've got a vector, right? X is a vector, an M by 1 vector. X is this. B has to be then M by M to make all this stuff make sense. Okay, so B is M by M. And so notice when you take X transpose is 1 by M. Oops, X transpose. And so notice when I take X transpose times X, I get 1 by M times M by 1. That's a 1 by 1. That's a scalar. That's a real number. When I take X transpose B, I have 1 by M times M by M. That makes a 1 by M. And then when I take that answer and multiply it by X, I get 1 by 1 again. So see, these are all real numbers. And so I'm saying I have a real number here that's equal to something, but also the negative of that something. That implies it had to be 0. So this product had to be 0. But remember, this product is x1 squared plus x2 squared up to xm squared. And that equals 0. Well, that implies that each of the xi's is equal to 0 for all I. Okay, and so there we have it. That's implied it that we get 0. And so that, A equal I minus B is non-singular. Which really, that's a pretty amazing result. That's a nifty result right there. Okay, and I guess that finishes out section 2.5.